Hi, I'm going to do a few formulas for you now. The first one I'm going to talk about, in this one, is that of a solenoid. This is a coil of wire. You've seen it in electromagnetic pickups and things like that. The word solenoid comes from, I suppose, the Greek or the Latin for tube, which has got into French, which basically means a tube. So it's a tube of wire or a coil of wire, and it has property. If you put current in it, it produces a field. Now you use the right hand grip, so the current is going over the top. At the top of it, the current going through the tube is going that direction. So if the current's going away from you, it's going from right to left, is one way of seeing it. Or another instance is that if the current is going clockwise, or so anti-clockwise rather around the page, it's coming out. So you just use your right hand to work out what's going on. And it's got a very simple formula, that B through the entire field. So if I have a solenoid, an infinitely long solenoid, it has a very uniform field across it. A constant field, and the field's B. It's measured in Tesla. That's the term for it. So B is the actual field that you measure. H is something a little bit different. Is the field that it's called the H field, or magnetization field is H. Magnetic field is B. A B is a field that you measure with a magnetometer. So you measure a magnetic field by how much, if you have the compass pointing east-west, how much it's going to turn is a way of measuring, or there's different ways of measuring a magnetic field. I'll give that a bit differently. But the formula is simply mu naught, that's the number we'll talk about, the number of turns, let me see, the number of turns times the current divided by the length. So it's the number of turns per unit length going up. Now this is quite surprising. So the actual size of the coil doesn't matter. It's so it can be small, it can be big. It's the number of turns per unit length. Now obviously it's going to be a lot less wire getting 100 turns per unit length in something small. If it's something big, it takes, say if it's twice as big, it's got 4 times the length of wire. The formula comes from basically Maxwell's equation, which basically says exactly that if you integrate the current around the outside, you get the magnetic flux going through the space in the integral. It comes off. This is one of Maxwell's equations. So there's where is the basis of it? It sort of comes from a bit of geometry, but also comes from just the basic nature of space. So our space is a space for which Maxwell's equations operate. And it's sort of a bit of a circular argument. So let's go through it again. It's B equals mu naught N I, the current per wire, divided by the number of wires divided by the length. That's basically a current density. Number of wires divided by the length times the I is the current density, and that's basically Maxwell's equation. Now mu naught, let's have a look at that. That was, it's 4 pi by 10 to the minus 7. It used to be that number exactly, and you're going through the equipment, the original things. Ampere did some experiments and determined what a Newton was by current, and so this is one number. That all the other numbers had the variables with it, but this one actually was an exact number. And so it often used to upset me in the HSC exam papers. They would give this number, that version of the number, as 2.0 by 10 to the minus 7. However, it's an exact number, so you don't have a 0.0 with it. But now that has changed. So mu naught is 4 pi by 10 to the minus 7, almost to an exact amount, because we've now changed our measurement of mu naught, not from an experimental measurement, but from the measurement of two space constants. One is the fine structure constant, which is roughly 137. There's a combination of the electric charge, which is something which is measured, and also Planck's constant. These are basic units. So since 2019, which is just last year, we've swapped over to a slightly different mu naught. All the equations are exactly the same. So just let's go through that solenoid again. A solenoid is a tube of wire, and a tube of wire having n turns per unit length times the current gives you mu naught n I on L, gives you the magnetic field through it. I'll have a bit of a talk a bit later about actual real solenoids. That's an imaginary solenoid that you will have in your tests to work out.